Hey everyone, another day, another DSA problem. So today let's look at 1081. That's smallest subsequence of distinct characters. Okay, so this is very straightforward, the question at least. It says you're given a string S and you have to return the lexicographically smallest subsequence of S that contains all the distinct characters of S, exactly ones. Okay, so they've given me an example here, BC, ABC, right? So if I have to look for something that's the smallest, when they say lexicographically smallest, that would mean if it was coming in a dictionary, which one would have come first, right? So let's look at BCA. Okay, this has all of the characters, but is that the smallest? No. We have CAB, is that the smallest? No, that's basically, it comes after BCA. And then we have ABC. So ABC has all of these distinct characters and it would be the smallest. So that's our answer. All right, so that's pretty straightforward. I think we can just go ahead and try to understand it further and see what our solution can actually be. Okay, so as we see, we're given a string S. So let's take an example here, KVASBK, okay? So we want to return the lexicographically smallest subsequence, right? That contains every distinct character. So our distinct characters here are K, it's B, and then it's A, and then we have S, right? So I can just look at this and say KBAS is like, it has all of those, right? But is that the smallest, right? Let's keep that as one of our options, right? And then we have BASBK, so that won't be it. It could be BASK, okay? This also has it. And then we're going to see from A, okay? So we have ASBK. So amongst these, which qualify because they have all of the distinct characters at least once, this is the smallest, and that's why it's the answer, okay? So the brute force approach to solving this would be to actually go ahead and generate all our subsequences, but we know that it's going to take 2 raised to n time, right? So that is something to consider. So we can go ahead and generate all of the subsequences. Then we can keep only those which actually contain the distinct characters, right? Like what we did here, but we actually generate all of them and check this. And amongst those, like the same way we compared over here, we're going to compare and then we're going to find the smallest. So this is something that can be done as a brute force approach. But as I said, it's going to take a lot of time and that is not optimized at all. So, so generating subsequences itself is the dominating factor here, which will take O of 2 raised to n time. And with a very large size n, that would be too much time. And then all the other steps we mentioned over here. So yeah, you can see that's not very optimal. So the question is, how can we optimize it, right? So let's look at this. There are 2 observations which are worth noting over here. So we actually have 2 goals, right? So one thing is every character has to appear exactly once, right? Exactly once. And then the answer should be the lexicographically smallest. So these are 2 things that are most important to us. So can we build around this to come up with a solution, right? So one thing we can do is, so let's traverse through the string. And whenever we find a smaller character, we're going to see, can I place it earlier in the answer? Okay, so that's just a basic intuition. So we'll see how we're actually going to do this and implement it, okay? So here's the key idea of how to solve this problem. All right, so we're going to maintain a stack because the stack is very useful when we want to, hold kind of monotonically increasing or decreasing sequences, right? So we're going to use a stack, and this stack is basically going to represent the current best answer that we have. All right, and we're going to start building up on the stack and keep changing it to see like what our eventual answer is going to be. And here's what we're going to do. We're going to iterate through the string. And whenever we see a new character, we're going to ask ourselves, can I improve the answer that I currently have by removing some larger characters and swap them with the smaller character that I've found? Okay. I know this might sound a little confusing. When we do a dry run, it will be more clear. I just want to lay down these rules, which we will be following later. Okay, so as I mentioned, we ask ourselves this question, can I remove something from the stack, right? And you know that the stack is like last in, first out, right? So I can't remove things from the middle. I have to remove them in a certain order. So when can I actually remove something? We need some kind of case for this, right? So you can only remove something from the top of the stack, as in your answer, which was actually the last element that would have appeared in our answer sequence, is if that top character is greater than the current character that we have, all right? And let me give an example. Let's say we had a stack over here. We had something like B, and then we had something like K. So K was on top. And then let's say our string was B, K, A, S, or something like this, okay? So now I've come to A. And that's when I check the top character, is K larger than B, larger than A, right? K larger than A, yes it is. So what I'm trying to do is I'm trying to replace those larger elements to replace them with smaller elements because I want this to be the lexicographically smallest string, right? Subsequence. Okay, so then I check, is K greater than A? Yes, it is. Okay, so I can remove K and I can replace that with A, but according to our condition of what we want, we have to have all of these characters appearing at least one, like not at least once, exactly once, right? So if I remove K, it's going to be a problem if I never see K again in the near future, right? If there was a K later, then it's fine. So I'm not going to blindly just remove K just because it's greater than A, okay? I want it to be greater than A, yes. But I need to make sure that the top character appears again later. So I need to be guaranteed that a K exists after this position so that I can add it back to get my resultant answer, all right? And if both of these conditions satisfy, then we're going to remove the top element. You're going to say, hey, we haven't visited this element. We can, this character, we can visit it again sometimes. So if both of them are true, we're going to pop now, and then we're going to add later because it's possible to add it later. Or else we're just going to keep it, okay? So let's say K was never there, then we are not going to remove K. We're just going to keep it as B, K, and then it would be A and S. Because if I had removed K, then B, A, S would not be a valid answer. All right, so there comes the question, right? So how do I know that K actually appears later on, right? So we can keep something like a write count, okay? So let's traverse the string once and let's keep a count of all of these characters, right? So then I would know that, okay, K has appeared twice, meaning if I'm at some position and I know that there's still values of K later on, I can utilize them. So let's keep something as a write count, and it's going to denote how many copies of the character are still left to process, okay? And this has to be accurate according to each position we go to, because I need to know from this position to the right, are they present? Because if I'm just considering all of the count, then it could be values that were to the left, and I would have rejected those, like not taken them, right? So every time we read a specific character, I want to update its write count, because if I'm at this position, then everything to the left, including itself, is not part of the count. We only want the write count. So this is very important. So when I come to this position of A, my initial count of K would have been 2, but after I go to this, okay, let me just write it here again. Okay, so it was B, K, A, S, something like this, and then a K. Okay, my initial count of B was 1, count of K was 2, A was 1, and S was 1. So when I come to B, I'm going to reduce B, make it 0. When I come to K, I'm going to reduce it, make it 1. And then when I come to A, so K was on top of the stack, right? If I want to remove K, I would then check, is K actually present in the future? And yes, it is. But if it was 0, then I want to keep K there because there is no valid answer possible if I remove K. That's something there. All right, so we also want to see, it could be the case that I visited some element. Let's say I visited B already, okay? I don't want to go ahead and visit it again, right? If it was my optimal visit, right? So we need to know when a certain element is visited, right? So for the same example, B, K, A, S, A. Okay, A has already appeared. So when I go to this A, I don't want to add it to my stack again. I just want to skip it. I don't want to visit it at all, but I still need to decrement its count, right? So that's why we need something as a visited, because if something has gone to the stack, and we have considered it as part of our answer, that means it has been visited. Okay, so we need to keep track of that. So yeah, if it's true, if it's already visited, then we just skip it, or else we're going to visit it now. Okay, great. So I think this was pretty understandable already, but let's just do a dry run of this example to understand. Okay, so the first thing, as I mentioned, we do our first pass. First pass where I'm going to go ahead and actually count everything to the right. Okay, so how many counts of B do we have? We see 2. And then for C, we see 2. And then for A, we see only 1. Okay, so now let me have a stack over here, and I'll go on traversing elements. Okay, so the first element, I come to B. I'm going to add it to the stack because there's nothing in the stack. And I also want to go ahead and decrement this count because there's only one more B left to the right. Okay, then I'm going to come to C. So I check my stack. All right. C hasn't been visited, by the way. I need to consider visited as well. All right. So once I visit B, I'm going to mark visited for B as true. And C is not visited. A is not visited. Okay. So when I come to C, it's not visited. So I will process it. Then I'm going to check my stack. Was there something I could have replaced which was worse than C? Okay. And B is smaller than it. So no, that's not the case. So I'm just going to add C. Then I'm going to mark that C was visited. All right. And I'm also going to decrement the count of C. So I'll make it 1 now. Then I come to A. All right. Again, A is not visited, so I can visit it. So I'm going to check the top of the stack is C, and C is greater than A. Now I want to see, can I replace C with A so that I get a better answer, right? And for that to be true, C is greater than A, but we had one more condition, right? We wanted to see if the top character appears again later. So I'm going to go to this right count, and then I look at C, and yes, C does appear later. Okay, so I'm going to go ahead and I'm going to remove C from the stack. Okay, when I remove C from the stack, I want to go and say, hey, C has now not been visited, so I can visit it later. So this goes to a false. And yeah, so now the top of the stack is B. Again, B is greater than A. Let me go and check. Do I have occurrences of B that come later? Yes, I do. So again, B will also be popped out from the stack. And I'm going to go ahead and say, hey, if another occurrence of B comes, I can visit it. Now I'll add A. I'm going to decrement the count of A to 0. There are no more A's left to the right. And then I'll go to my next character here, which is B. Okay, so B is just greater than A, so I can go ahead and add it. So I'll reduce the count of B, make it to 0, add a B here, and say, let's remove this. Okay, say I visited B. Okay, then I'm going to come to C. C is greater than B, so I can just add C here, decrement the count of C to 0, and then I can say, hey, I have visited C. Okay, and A was also true. So if I turn this into a string, this becomes ABC, and this is my answer. Okay, so what exactly was our time complexity here? So let's look at that. We traversed it once, so that was an O of n traversal to count everything. And every time I go to the stack, I might be popping everything else out, right? So the total is I might add everything once and I might be removing everything again, right? So that could be O of 2n, let's say. So the total could be something like O of 3n, but we remove constant. So this is O of n, right? And our space complexity, since we are using a visited array for that, and then we're going to use the right count, right? So this would be something like, let's just actually convert our characters to their numerical forms, right? Like A is 1. So we'll have 26. So O of 26. So I can say this is just O of 1. It's constant. It's this. Okay, let's go ahead and just code this up. Yep. Okay, I've already written the code, but a few people have requested that I write it out while I'm teaching, so it's easier. Okay, so what did we have? We had visited. So let's mark that into 26. And then what else did we have? We had something called a right count. So let's do the same thing for that. to 26, then our, pass one, traverse, and store right count. Store right count. Okay. So let's go ahead for character in string. We're going to do right. Let's find the index of that. Let's convert it. So the index of that would be the word value of that character minus that of A. Okay, so now we have that index, and let's go ahead and update the right count for that character. Right count of that index plus is equal to 1. Okay, then we were considering a stack for our answers. All right, so let's go ahead and do our traversal again this time. So for character in S, okay, so we had a condition there. One thing we were checking was, first let's just do the index calculation. Again, I think I can just copy paste this here. All right, so the one thing we were checking was, have I visited it or not? So let me check that. If it hasn't been visited, then I want to process it. So if not visited of this index, then I'll just do something, or else, or else I don't need to go to that loop at all. But there was one condition, right? So whether or not any of this takes place, we did want to decrement this right count as we were traversing through the string, right? So I want to do that as a default, irrespective of whatever happens. So I want to do right count as character minus is equal to 1. Okay, so now we can just look at what happens when it's not visited. Okay, so what were we doing? If it's not visited, then I want to check one thing. All right, I want to see is it a better replacement for something that's already in the stack? Okay, so I want to check that first. So while stack and typos. While stack and the top of the stack is greater than the current character that I have, then let's get the top index, okay? So top index would be board of stack of -1 minus board of A, okay? While it's greater than that, okay, if another occurrence if it does exist, right? Remember that condition. So if right count of that top index is greater than 0, then I can replace it. Then what do I want to do? I want to say, hey, I want to remove this as having been visited so I can visit it later. So visited if this top index is going to be 0 again. And I just want to do a stack.pop. All right. Stack.pop. Okay. Or else, let's say it's not present again. Okay. So one thing is, if it's not present again, I cannot continue because if I'm not removing that element, I don't just want to continue and keep removing other elements because the stack does not allow that. So if that's not the case, then I just want to break. All right. And one more thing is I have to mark this as visited. So I want to do visited of my current index is going to be equal to 1. And I want to go ahead and add it to my stack, right? So I want to do a stack dot append character. Okay, I hope this is correct. So let's just check it once. Okay, I'm taking the index. I'm checking if it's not visited. How can I replace it on the top of the stack? That's only if the top of the stack element is greater than it. Okay. Get the element count of that to the right. If there are more of it, then I'll say I'm not visiting it. I'll remove it, or else I'll just remove that. Whatever it is, at the end of this, I still want to say I have visited this, and then I want to append it to the stack. And irrespective of whatever happens here, I still want to decrement its count. Okay, I feel like this is right. So at the end, all I have to do is just do a join on the stack, and that should work. Right, okay, this is index, not CH. Okay, great, it's working. All right, so let me just go ahead and write the time complexity was what? It was OFN and the space complexity was also OFN. So yeah, this is the solution, and yeah, it's a nice problem. I hope you guys understood it. So yeah, happy coding, everyone.